Okay, so this is just the introduction. So the book that we have referred as a textbook, you can find most of the content there. So before going to the digital control, let us look at the analog conventional control. And then actually based on that, we can discuss why we should go for the digital control. What are the advantages or the applications? Okay, so in classical control, whatever or conventional control, what we see is something like this. A common block diagram you generally have seen hundreds of times, something like this. Okay, general conventional analog system. G of S is your our plant, and H of S in general is a sensor feed in the feedback path. Whatever the output that we are getting, we try to sense that one, and then we compare with some reference input. Most of the thing you already know. Then we have a controller. Okay, so controller is most of the time it don't have the enough strength, signal strength or power to drive the plant. So that is why we have an actuator or a driver. So this is the analog system. So the one example of this analog system can be in power electronics. You have studied, I think most of you have studied the buck converter. So if you have a buck converter, the objective of the buck converter is to lower down the voltage in the output side. So we have something like this. Okay, so this is the converter itself. Then we have to measure the output voltage. So we should have some controller like this. Here we will have our sensor, that is a H of S. Then we have to compare with some reference value. So in general, whatever the output voltage that we are looking for, something like that, V0 ref you can say. Then you should have a controller, C of S. So in general, we want to minimize the error. So that is why we use a PI controller for that. And then the MOSFET should be driven by some actuator or driver circuit. So this is a practical example of the control that we are doing in the analog system. And also the controller. By mean of the controller, what we actually mean is a combination of op-amp plus some passive components, in general, basically resistor and capacitor. Okay, so you don't have to understand what is the buck converter is doing or what is happening, just an example of what is happening. And if you go a bit detail, what you're going to see inside this PI controller basically is you should have a op-amp, a voltage divider network that is actually sensing your output voltage, that is H of S that we are sensing. And then you should have your reference VREF here, or V0ref, whatever you call. Okay, so now the controller part. So you should have a controller like this, a resistor, capacitor, and then a capacitor network. This is actually a PI controller, type 2 PI controller. And this actually introduces 2-pole and 1-0 to the system. Again, you don't have to worry too much about this, how this works. because you can find this thing in your power control system engineering book that is Norman S. Nice's book in the chapter 9, at the end of the chapter 9. So if you are interested, you can see there, but just what about this two plus and minus that you're seeing? These are actually nothing but this summing junction that we are having here. So basically you actually can relate what is happening in the analog system. Now in the analog system, why you are calling it analog? Because throughout this operation, the signal that is flowing in the control system is 100% continuous time, and they're coupling one controller circuit to the planned circuit, and there is no time delay. So 100% continuous time signal. Number one, there is no time delay. Time delay will be introduced because of your digital circuitry, and also there is no sampling delay. Okay, and the error that is been produced due to the quantization, that is also not present. Okay, so this is why this is called analog system or continuous time system. And now compared to the analog system, how can we actually discuss about the digital system? Okay, and before that, why actually we should go for digital control? So why digital control? Okay, so one advantage of the digital control is that it removes, or it actually takes away the disadvantages of the analog or continuous time control. What are those? The disadvantages. The first disadvantage is discrete analog component. So whatever the PI values, or actually proportional gain, P values, and then you have I values or KP, KI, those coefficients. According to that, whatever the circuit that you are implementing, that is fixed. And if you want to change these values, then you have to change the entire circuit. So these components, the resistor, capacitors, every time you change the value of the KP, KI, every time you have to change the values. So one of the disadvantages is discrete components. So discrete analog components. So which needs to be changed every time you change the values of the system parameter. This is one disadvantage. And then the second disadvantage is analog components with time, they actually degrade. So degradation of analog components, and at times with temperature, especially with temperature, you'll see that component damages as well. Okay, so, and also what you see is sometimes the system itself changes. The system's time varying system that we're talking about. So some parameter of the system changes with time. Like if you consider the fuel in a satellite, or maybe if you have a missile going on, whatever the fuel that is inside that one. So with time that is actually depleting. So those are actually changing with time. So with dynamic system, whatever the analog component you have, it cannot adjust with that one. So this is one of the problem with the analog system as well, is that it cannot actually adjust to time varying system. Okay, so, and also finally, since in some complicated system, it may happen that the feedback that you are applying may have multiple loops. So multiple loops means multiple op-amp, multiple capacitor, resistor networks. So basically the size will be large. It will be difficult to implement, and also cost is another aspect, since a lot of equipments that you are using, so they will be expensive as well. So that is why it is difficult to actually go for the, these are all disadvantages of the analog control system, and because of those we should actually go for digital. To overcome these problems, you should go for the digital control. A simple digital controller can be something like this. So same circuitry. What we are doing here is we are introducing the controller, which will be a computer or a microprocessor or some DSP, that is digital signal processor. So those can be there. This is something like this. This is G of S. So this is your output Y of S. So in the feedback, what we are having is H of S is still your sensor. Now what we are changing here is we are introducing a sampling circuit. So sampler is there. And because of the sampler, I think it should be something like this. So this is what is called zero order hold, or some other order you can take, but most commonly zero order hold is being used. So now here your controller is being changed. Controller is changed, and what we have is CZ in the Z domain, and this portion of your controller is driven by the digital signal. So basically this portion we call digital control. So as you can see, the whole portion of your system will not be digital, rather it will always be a combination of the digital and analog. Okay, so this portion, that is plant and your sensor, will still run by the analog signal. Then whatever the sampled voltage that or some other value that we are getting, that will be actually sampled. And then this reference now also has to be your digital reference. So you should have RKT, and you may have YKT here. So discretized values, so error, EKT, with the sampling period of T. Okay, then whatever the controller value you are getting, that you can call it, this is UKT. And finally, with the zero order hold, because the plant cannot be driven by a discrete signal or digital signal, so you have to have a zero order hold, and ultimately it will be your control signal, a continuous time signal of some sort. So that will actually drive the plant again. So this is actually a simple digital system. And here what we are seeing is that this one CZ, this can be actually any microcontroller or microprocessor, or it can be DSP, that is digital signal processor as well. In IoT, we have one processor in machine lab, so DS1104, I think. So that can be used for the research as well. So what is the advantage? The first advantage is whatever the control, PID or PI, whatever it is, or adaptive or any other model control, nonlinear control can be implemented using the codes. So you just write the codes, MATLAB in general. The MATLAB, you write the code and that controller will be designed accordingly. So basically, the advantages that we are going to get is they're flexible because you just change the code accordingly, your controller will be changed. So same piece of hardware can be used with different version of software for implementation of the design for in different applications. So this is one of the great advantage of our digital control system. And secondly, since you just have a simple single microcontroller or processor, it will take less space as well. And changing the code is the implementation time will be lesser, it will be less expensive, and the tuning will be more frequent. So flexible tuning is also there. So all these advantages, and also if you want to have nonlinear control or adaptive control that can be applied for your time varying system, all these things actually can be implemented using this digital control system. So as you can see, a lot of advantages are there. So we should actually study this thing and try to implement the digital control instead of the analog control. But as you know, nothing is free. So you have to pay some price if you want to go for digital control. You know, what is that price? The price is basically complexity is more. You have to know a bit of digitization and what are the problem associated with this digitization and how to implement or counter those problems so that actually we can go for this digital control system. So a lot of study, a bit of hardware implementation and software programming learning. So all these things will be coming along with this lot of flexibility of control system design. So this is the question that you should know why you're going to study this one is basically is covered in this portion. Now, this is a common block diagram of a digital control system. Again, as you can see, in some part of it, you will have continuous time signal, and some part of it, you will have a digital signal. So in this one, let me explain step by step individual things. So as I already said, the advantages are clear. So you can just change the code in the microcontroller or the computer. Accordingly, your programming will be changed. So flexibility is one of the great advantage of this one. Now, let us define some, and what is our objective? And again, our objective is as before, what it was in actually analog or say classical control system theory. That is, we have to have a plant and the dynamic response of the plant has to be changed, actually has to be fulfilled, whatever the response, specific response you're looking for. And it has to be by means of a digital implementation of your analog one. So whatever the knowledge we already have from the classical control theorem, so that will be also useful. So you should have a clear picture of that thing as well. And now what we are doing here is how to actually discretize some part of it so that we can take the advantage of the computer or the modern technology. Okay, now let us define few things. What is plant? You already know. A physical process that whose satisfactory response requires control action. That means, what do you mean by satisfactory response? Is basically suppose we are tracking or following some reference input RT. So basically, our output that YT will try to follow RT. So this is what is our objective maybe. And for that, this one needs to be controlled. So this is our simple objective. Now, what are the problems there may be? Number one problem in the tracking is maybe the plant itself is time changing. So with time, the plant itself is changing. So with a changing plant, whether our system can actually still track the reference input or not. If it can do it, then we call it is a good disturbance rejection system. Okay, so WT is a disturbance that is going to the plant. Even with the disturbance, our controller can actually track the reference input. So we should say that the controller is having a good disturbance rejection. So good disturbance rejection. Okay. And now if the plant itself is changing, okay, but still our controller works, and then we call that system as a low sensitivity. Okay, sensitivity. So two things. One is we have disturbance. Still we can actually track the input voltage. So this is one thing. The system itself is changing. System is changing, but still we can actually control or regulate the output. So in both cases, if both of them are achieved together, then actually called is robust control or robust regulation as well. Okay, so this is what is done. What is the definition of the robustness? So it has to be low sensitivity. The sensitivity has to be low, as well as the disturbances or the noises that can be associated, like this one in the sensor also we have disturbance. In the plant itself, we have some disturbance or noise, but still the output can follow the input. Then we call this one as a very robust system. Okay, now what we are actually introducing here is ADC. Okay, so whatever the sensor output that we are getting, okay, even after the disturbances, what we are getting. So basically we have a ADC. So inside the ADC, by default, there is a sampler always. Then we have ADC. So combination of these two is actually represented in the block diagram as ADC. So discretization is done by the sampler. Then a digital coding is done by the ADC. So basically we are getting a number sequence from here. So what should be the size of the number sequence? It actually depends on the size of your ADC, whether it is 8-bit or 16-bit or 32-bit. So higher the size of your controller, the ADC bits, the expensive it is. So you have to be careful about this one. So whether you want more precision, also if it is high bit ADC, then the storage size should also be higher. So whatever the data that you are saving, that will also require more space. So this is one common thing that you have to keep in mind. Now, what you are seeing here is whatever the signal we are getting is Y hat. Y hat we are calling it because it is not actual output. Actual output, along with the disturbances and some, because of this digitization, sampling and digitization, there is some quantization noise error as well. So after that, whatever we are going, there is actually some other value, not exactly what we are supposed to get. So there is some difference between these two. They are not exactly same. And also this is not exactly the error that it's supposed to have. The exact error should be R minus Y, but we are here having a hat to represent that this is actually a measured value of the output. Okay, so as you can see, this portion is basically our digital controller here in this diagram, this portion. And ultimately what we're trying to do using our computer is actually to get a discrete control signal, the coded discrete control signal. And then because the discrete control signal cannot drive the plant, so we should have a DSC controller. So a digital to analog controller converter. And also you have to keep in mind that digital to analog converter will always have a zero order hold. Okay, at least zero order hold should be there if it is not more complicated. So you always have to remember one thing: in the ADC, you always have a sampler, and in the DSE, you always have a zero order hold. So this is somehow what is meant by a digital control. But from time in different books, you are going to get actually uh, different block diagrams, but more or less this is how it has been represented. Now, next thing that you should know that what are the problems that we are actually introducing while we are digitization. We haven't talked about that. So the problem that we are going to get is mainly two things. One thing is sampling, and the other thing is quantization. So these are the two major problems that we are going to, that will be introduced in this digitization process. So sampling. So sampling, what type of sampling actually we have? Sampling. And what sampling is actually doing? This is one question. Sampling period. And the other thing is quantization. Okay, so how to actually represent this thing, and then how to actually use those in analog control system design. And once we can comprehend these two into analog control system design, then actually discretize that controller into digital domain, and then just writing the code according to the difference equation that we are given. So this is our objective of digital control system, one of the easiest way to do the digital control system design. Okay, so sampling, there is different type of sampling. Yes. Before going to different type of sampling, we also have to define different signals. So this is from your textbook basically. So there is signal is basically in two types. Number one is continuous time signal. Then you have discrete time signal. So in the continuous time, there is two types basically. One is called analog signal, and the other one is called quantized signal. So basically, if time is continuous as well as the magnitude is continuous, both are continuous, any value we can take in the magnitude and any value we can take in the time domain. So then it is called actually an analog signal. So, but if your magnitude is discretized or quantized, basically, magnitude is quantized, but in the time domain, it is still continuous, then we call it a quantized signal. Okay, so, but in general, we say interchangeably, basically, use continuous time as an analog signal, but there is another version. So quantized signal is also there. And also in this textbook, they'll be using interchangeably these two, but they are not actually exactly same. So analog signal is a part of continuous time signal, but all continuous time signal is not analog signal. Similarly, discrete time signal has also two versions. So one is sample data signal. In this case, the magnitudes are actually continuous. It can take any value in a range. Okay, so magnitude or amplitude is continuous, and only the values are taken in the specific times, so t, 2t, 3t, something like this. Okay, so time is actually discretized, but magnitude, it can take any value. So that is why it is called sample data signal. And if it is quantized as well as discretized, then we actually call it digital signal. Okay, so digital signal. So both of them are actually discretized, magnitude-wise as well as your time-wise, even though it should not be discretized. So time is discretized and your magnitude is quantized, then we call it digital signal. So in a control system, in different portion, how the signal flows, this is what is being shown here. So output is a continuous time signal. Input is a continuous time signal. As I said, in different book, they will have different version of it. So this is according to your Ogata book. This portion is basically the digital control. Okay, so this portion is your digital control. Now look at the signal flow. So reference is also continuous, output is also continuous. So whenever the error is generated, error is also continuous. Now error has been actually discretized using a sampler, and then you have a ADC, then you have digital values. Computer will process the digital values, then it will also generate a digital value, then you will have a value, paused value basically. Okay, so now these values cannot be directly applied to your controller, so that is why you actually have to hold the values. So you'll have something like this. So this is the function of the hold circuit. So now we have a continuous time signal that can be made even smoother, like a pure continuous time signal or analog signal. To be specific, then you can drive the plant. Okay, so this is how the signal is actually been flowing in a circuit. And this is also one of the example of your digital controller. As I said, in different book, they will have a different version of your digital controller. More or less, controller segment, even before or after the error signal is actually being used as a controller. So some slight variation is always present in your control. Okay, so what are the steps of this course? So a great portion of the course will be actually will cover the Z transformation. Z transformation. Then we'll try to understand how the system that has been designed in the conventional or classical controller can be used to generate the CZ. So this is also will be a one implementation thing. And once you can do that, then you have to have a equation that is UKT, that is difference equation, not differential equation, rather difference equation. Then this difference equation will be implemented in a computer, microcontroller or microprocessor or DSP. Okay, so this is our objective of this course. And eventually what we need is, if you have a certain reference value given, we have to have reached to that steady state value with satisfactory performance, even with those digital components. So two problems for us is sampling. Okay, so sampling period that we have, how to implement this thing in the analog controller, as well as quantization. Okay, so we have to somehow cope up these two in our classical control theory. Then using this one, we actually go for this methodology. Eventually, we have to achieve our satisfactory result, that is dynamic response that we are looking for. Okay, So more or less, this is our introduction. And if you have any question, I can answer. Otherwise, let me stop here.